Okay, now we will see some important properties which are required for the governing equations. The first one is say density, then dynamic viscosity. So, momentum equation has this, then thermal conductivity energy equation has this, then the specific enthalpy of the mixture, then specific heat at constant pressure Cp, then the mass diffusivity, okay, for calculating diffusion velocities. So, these are the important physical and thermal parameters involved in the governing equations. Okay. Please understand that these properties depend on temperature very strongly, because of the significant temperature gradient which we see in the reactive flows. We have to calculate the properties as a function of temperature. So, that will give accurate results, but there are several approaches where we need not do that. We can calculate the property at an average temperature. See, for example, if flame temperature is Tf, okay, so flame temperature say T suffix f and the ambient temperature is say T infinity, you can take some average temperature in between this, okay, some average temperature and calculate the properties at this average temperature, that is also fine. But it may not work for all the things. So, for a predictive model normally you take the flame temperature, okay, and the ambient temperature. The temperature varies in between these two, correct, Tf to T infinity. So, as a function of temperature calculate all the properties. The properties which are strongly dependent on temperature are calculated as a function of temperature. Okay. So, now the mixture properties are calculated based upon the concentration of the species in the mixture. So, these are the two things which actually we have to say. So, this is the comprehensive approach we do this. So, for density, as I told you, use the ideal gas equation of state. So, P equal to rho R T. So, this is the mixture specific gas constant, okay, then this is mixture. The pressure temperature is known, this is calculated as what? So, the R can be, R will be equal to Ru by molecular weight of the mixture. So, you know the mixture's molecular weight. So, universal gas constant divided by the molecular weight of the mixture will give you the specific gas constant of the mixture. So, you can use that and calculate the density rho. Okay, so, ideal gas equation of state is used for that. Okay, so, mixture molecular weight will give you the specific gas constant. So, that is what I have written here. Similarly, the dynamic viscosity mu, thermal conductivity, specific enthalpy and the specific heat of concentration of each species. First of all, you have to calculate. So, before arriving at the say dynamic viscosity of the mixture, we need to know the viscosities of each species. So, it should be calculated as a function of temperature. So, there are correlations available. So, you can take any standard property textbooks like Residual, okay, and you can get the correlations. There are a lot of researchers have worked on correlations for calculating the properties. So, see, one of the important book is Redital, R-E-D, Redital. So, this gives the properties of gases and liquids and as a function of temperature, pressures. So, in low pressure regime and high pressure regime and so on. So, a lot of correlations have been listed here and research papers can be used to calculate the properties. So, the dynamic viscosity, thermal conductivity, specific enthalpy, specific heat at constant pressure of each species in the mixture are calculated as a function of temperature first. Okay. Then mixture property can be calculated using the concentrations or mass fractions or mole fractions, whatever, of the constituents. So, now we are incorporating both temperature dependency plus the concentration or the mass fractions of each species. Okay. Now, what about mass diffusivity? Binary mass diffusivity Dij, binary mass diffusivity of pair of species I and j can be calculated as a function of temperature and pressure. So, once you know this, you can calculate the diffusion coefficient. Okay. So, once the diffusion coefficient is known, you can calculate the diffusion velocity. Similarly, thermal diffusion coefficient also can be calculated using some correlations, and using the thermal diffusion coefficient you can calculate the diffusion velocity due to thermal diffusion, Soret effect. Okay. So, diffusion coefficients for the mass transfer, this is the mass diffusivity. So, it can be binary diffusivity or di to m. So, some mass diffusivity say d, and not dynamic viscosity, kinematic viscosity, which is nu equal to mu by rho, okay, and the thermal diffusivity alpha, which is this is lambda is the thermal conductivity divided by rho density into Cp. So, lambda by rho Cp, that will be the thermal diffusivity, which you designate the symbol alpha for that. So, nu, d and alpha are the diffusion coefficients, and the unit for them is meter square per second. Okay. So, diffusion coefficient. So, this diffusion coefficient have the unit of meter square per second. So, you can see that based upon the species, the mixture, etc., these properties will vary. So, they may not be actually same, but so what we can do is we can actually define some non-dimensional numbers based upon these three. So, the first number what we define is called Lewis number, LE, Lewis number, which is the ratio of the rate of energy to the mass transport, alpha by d, that is the Lewis number. Okay. Prandtl number is a familiar number, it is the ratio of the rate of momentum to energy transport, that is nu by alpha. Okay. The third number is Schmidt number, where it deals with the ratio of rate of momentum to mass transport, that is nu by d, Schmidt number. Okay. So, SC. So, LE, PR and SC are the three non-dimensional numbers which actually deals with ratio of any two diffusion coefficient at a time, and that will be a non-dimensional numbers. Okay. Now, basically these numbers need not be the same. Okay. For example, even the alpha, nu and d are different, and we can say that these numbers will not be same. Lewis number can be different, and Prandtl number can be different, and Schmidt number can be different, but commonly what we assume is these are all the same. So, this is one of the assumptions we make. Basically, we make this assumption Lewis number is equal to 1. That assumption we make to simplify the problem. So, that we will see later how to simplify the problem by assuming Lewis number equal to 1. So, when you assume these all the three non-dimensional numbers are unity, then what we actually assume is that diffusion coefficients for mass, momentum and the energy are the same, that is d, alpha and nu are the same. Okay. So, d is equal for all the species. We also assume that the specific heat is same for all the species in several simplifying approaches. When you want to do a comprehensive analysis, we actually vary all the properties as a function of temperature and arrive at the mixture property by using some mixing rules. Okay. But when you want to simplify the problem, okay, the non-dimensional numbers Lewis number, Prandtl number and Schmidt number have been assumed as unity, and the d, the diffusion coefficient of all the species, okay, into the mixture is same, and specific heat also is assumed to be same for all the species. So, these are the assumptions which we invoke. So, why we invoke? Because to simplify the problem which is otherwise complicated. Okay. Now, let us see when there is a combustion phenomena, what are the controlling aspects that. Okay. There are three categories controlling the combustion process. What are they? First one is a combustion phenomena can be primarily controlled by using chemical kinetics only. The rate at which the reaction, okay, takes place, that will control the combustion phenomena. So, this is the first category. Okay. Examples for this category is when you do ignition, when you have a pre-mixed fuel and air and you try to ignite it. So, almost a uniform mixture is prevailing here, it is at a uniform temperature. So, everything is uniform here, only when you ignite it, what happens is the rate at which the reaction occurs, that will be the rate at which the mixture is depleted. So, ignition. Similarly, there is a pre-mixed charge in a constant volume vessel. So, now if you ignite it, pressure builds up and it explodes. So, the explosion. Similarly, when the flame is propagating, it may extinguish. Okay. So, the extinction, flame extinction, or when the flame propagates through very small diameter tubes, then it may be quenched. Okay. It may lose heat, okay, more than what it generates, so it may be quenched. So, these are the phenomena. So, the extinction basically depends upon the convective flow plus stress, the stretch of the flame, etc. The quenching is due to the heat loss from the flame towards the ambient, so on. So, when you want to capture or analyze these phenomena like ignition, explosion, extinction, quenching, etc., then you have to understand that these phenomena are predominantly controlled by chemical kinetics, category 1. So, we do not need to understand anything else, we need to focus only on the chemical kinetics to understand these phenomena. Second one is the combustion phenomena controlled by physical mixing processes. Okay. How the reactant species like fuel, oxidizer are mixed. Okay. Okay, how they are supplied first of all. So, whether the supply is very slow in nature, for example, very slow velocity, the reactants are coming in, so that the diffusion process is going to control that. Okay. Similarly, if there is a very high speed flow or the flow is laminar or turbulent, these things, okay, these are all physical mixing process, diffusion between two species, allowing them to mix. Similarly, a flow of a reactant, say fuel and oxidizer coming and they mix, due to the flow of them they mix. Similarly, turbulent the vertices of different scales which is present in the turbulent flow, that will increase the rate at which the reactants are mixed. Okay. So, the physical mixing processes would control this second category of combustion phenomena. Here examples are flames from gaseous fuel jet. Okay. So, for example, I will tell you this, I will draw a burner. So, this is the burner or a nozzle, okay, through which fuel is fed. So, F is the fuel, yeah. So, fuel is fed through this and fuel comes out. When it comes out, basically it takes in air. So, this is the fuel stream F, and the air stream from the ambient, entrains into this fuel jet and mixes. So, somewhere in this layer, what I am drawing here, what you get is well mixed, stoichiometrically mixed reactant. So, some fuel and required oxygen is available at this portion. When you ignite this, you will get a flame. So, a flame will be formed. Okay. So, this is the gaseous jet. A fuel jet is coming out, only one, there is no mixing, there is no pre-mixing here. Okay. Only fuel is coming out of a port or a nozzle, and due to the momentum of this jet, fuel jet which is coming out, the air from the ambient entrains into this. So, physically you can see that the entrainment is due to the momentum of the jet which is coming out of this into the ambient, which is not having any flow. Okay. So, by diffusion, predominantly by diffusion, what happens is there is a mixing of fuel and oxidizer. So, physical mixing process due to diffusion. Okay. Now, similarly there is a, so if you have a liquid fuel spilled on a surface or anything, you can ignite it. So, it will have a diffusion flame over this. That means the fuel will vaporize and that will contribute to the flame which is formed. Similarly, air from the ambient will come the other direction and mix. You can see that the rate at which the fuel vapor and the air from the ambient mixes, that will control the phenomena, combustion phenomena. Okay. So, that this we can say one example. And the droplet, spray of droplets, if you inject a liquid jet at high pressure, it will disintegrate into small droplets, and each droplet will have some flame over it. For example, the droplets are bigger enough so that some vapors are formed over the surface and they mix with the ambient air, and a flame can form over the liquid droplet itself. So, this again, the rate at which the vapor is going to mix with the ambient air, that will control the process. Similarly, the combustion of a carbon particle or burning of a candle is the best example we have seen. Is the burning of candle, that is a flame where you do not have any dependency on chemical kinetics, a little bit dependent only. The predominant control is due to the physical mixing processes. candle, first the wax should melt, the molten wax should vaporize, and that vapor should mix with the ambient air, and that will form a flame. So, this is what is the second category, where the chemical kinetics is not going to control, because that is very fast. So, which is slow will control. What is slow process here? The mixing, the physical mixing of the reactants, that is a slower process. So, that is going to control the entire combustion phenomena. Okay. Now, third category obviously is the combination of these two. In some cases, we cannot neglect kinetics, or we cannot neglect the physical mixing process. In the first case, when only chemical kinetics is going to control, I do not really need to worry about the mixing, because already the reactants are mixed. Mixing has already taken place. Similarly, maybe the mixing is very fast, so that the mixing time is very fast. So, that is not going to control. The chemical kinetics, the rate at which the reactant burn is going to control. So, that is the first category. Second category here is the mixing process is slower now. So, the kinetics is very fast. So, the flame has formed, but the flame has to really form based upon the location where the fuel and the oxidizer are going to mix at the stoichiometric proportions. So, that is the second category. Third category, controlled by both kinetics and physical mixing. Okay. So, now for this, the example is given as Bunsen burner or a gasoline engine, okay, spark ignition engine in automobiles, or partially premixed flames. So, for example, in Bunsen burner, what happens is, this is a Bunsen burner. So, this is the fuel supply orifice or nozzle. Okay. Through the nozzle, fuel is supplied. Okay. So, there are holes in the periphery of this is a mixing tube. So, this is the mixing tube. Okay. And there are holes in the mixing tube. When the fuel is injected like this, due to the momentum, high momentum of the fuel jet, the air entrains from the ambient. So, there are holes in the mixing tube. To the holes, the air entrains, and these two mix. The fuel jet entrains the air and mixes with the air. So, now what you see at the top of this tube, mixing tube, is a premixed reactant. But this reactant is not completely premixed as we see in the first case. It may be premixed to some extent. Okay. So, probably to the rich side, may have more fuel than the stoichiometric fuel value. Okay. So, this is the Bunsen burner case, where you allow the air to entrain and partially premix. So, we get partially premixed flames. So, in this both the mixing rate of the additional air which is going to come out here, the additional air is going to come in the top of the tube, mixing tube. This is the primary air. This is, say, I will say P and S. Okay, this is P and S. P indicates primary air entering into the mixing tube due to the momentum of the fuel jet. Secondary air will entrain at the top of the burner. So, both mixing and kinetics, both are important. Because of partially premixing, kinetics is important, because the additional air requirement, the secondary air is supplied, no, it is entrained again. It is mixing control, physical mixing will play a role. So, both kinetics and the physical mixing plays a role in the third category. Okay. So, that is, these are the three things we should understand. So, three categories of combustion are the combustion phenomena, which is completely controlled only by chemical kinetics. Second one is, it is controlled only by the physical mixing process, that is the rate at which the fuel and oxidizer are transported into the combustion chamber. So, that this transport process may not be only convection, it may be diffusion or it may be turbulent, everything. Then the third one, both are important. That is, there are some aspects which will need kinetics to involve, there are some aspects which will need mixing process to be taken care. So, both are important in the third category. Okay, now let us see. We have already seen what is called characteristic chemical time. We have already seen this. That is the initial concentration of reactants we know. So, the concentration of the reactant is reducing, okay, with time. When it reaches 1 by E of its initial concentration, it needs some time to do that. So, that is called characteristic chemical time T suffix C, the time taken by the reactant to reach 1 by E of this initial concentration at a given temperature. So, that will be the time of the chemical reaction, the time for the chemical reaction to occur. So, you can see that. So, chemical time we say. Then residence time is the second time characteristic time we define. See, for a reaction to complete, it should reside within the particular space for a particular time, correct. So, for example, when the reaction should occur at a particular say small control volume, So, see, for example, I take the Bunsen burner example. So, the mixture is coming, partially premixed mixture is coming out here, okay. So, now what happens here is you take a small portion here in the exit of the Bunsen burner. If the reactants which are coming out, okay, so there I'll say fuel plus air is coming out, some premixed thing is coming out. Okay, now here in this control volume, it has some length scale, correct? The control volume has some length scale. So, if the velocity of the fuel and air mixture is very fast, very high, okay, then what happens? The time the reactant resides in the small portion is very small. So, it resides for only a small time. But if the reaction is not able to complete within this particular small time, then reaction will not occur here, correct? Because it is not able to, reaction is not able to complete within the residence time of the reactant. So, that is very important. Second characteristic T suffix R is the residence time of the reactants. So, reactants should stay at a particular location for a given amount of time for the reaction to complete, okay. So, that is the second important characteristic. So, residence time. So, how will you calculate residence time? So, we know how you calculate the chemical time, we have seen already by using the first order, second order reactions, etc. We have definitions for the chemical time. So, we can use that. The rate of the reaction will be used to calculate the chemical time. Residence time you have to calculate. Okay, now there are two conditions. Okay, let us take a diffusion dominated transport. Okay, very low flow velocities. So, diffusion will dominate the flow. In such a case, the residence time, which is also called the physical time, is defined as L square by D, okay, where L is the characteristic length. So, as I told you, some length you have to take, okay. For example, in this case, Bunsen burner, it may be diameter of the tube, some length scale or height of the flame, that can be a length scale. So, some length scale, and the D is the mass diffusion coefficient, okay. So, this is the time, because L square by D will be the units will be, so you can see this meter square divided by, this is meter square per second, so which is equal to second. So, that will be the time scale, L square by the diffusion mass diffusion coefficient, that is the time scale which is called residence time in a low flow velocity environment where diffusion dominates. So, here diffusion dominates, so the diffusion coefficient is the important thing. So, when the diffusion coefficient value increases, then residence time decreases. So, when the diffusion coefficient value increases, that means the rate at which the diffusion occurs will increase, correct. So, that is rho d is the, when the rho d value increases, the diffusion rate of diffusion will increase, correct. So, when the d value increases, then the diffusion rate of diffusion will increase, but the residence time or the physical time will decrease, okay. Here, so here similarly in the chemical time also we know that when the temperature is higher, when the reaction rate is faster, very fast, okay, chemical time will be very low, correct. When the reaction is infinitely fast, the chemical time will tend to 0, correct. So, that is the chemical time. So, based upon the reaction rate, you can see the chemical time can be smaller or higher, larger. In the third, convection dominated transport. So, you have the residence time definition as the the characteristic dimension, again the characteristic dimension L, and the flow velocity u. So, this will be L by u, which is meter by meter per second equal to second. So, that will be the time. So, for example, there is a combustion chamber of say length L, that is the length I want to consider. Okay. Some reactants are coming in, fuel plus air, with a velocity of u. So, what is the time it will take, what is the flow time here for the reactant to reach from this point to the end of this, to cover the length L, what is the time? L by u. So, that is the residence time. So, for that time a reactant mixture will be residing in this. Okay, if we take a small chunk, this chunk will take the time of L by u to travel along the length L, okay, of this. So, this is the convection dominated transport. Physical time or residence time is defined as the ratio of the characteristic dimension L by the flow velocity u, average flow velocity. So, these are the time scales which we need to understand. So, chemical time scale which is dependent on the reaction rates, that is one of the time scale. So, that is actually the time from the initial reaction, start of the initial reaction, where the reactant concentration is going to be say A suffix naught, that reduces to 1 by E of the initial concentration. Okay. Then residence time for diffusive dominated transport or diffusion dominated transport will involve the dimension characteristic length or characteristic dimension and the mass diffusion coefficient is given by L square by the diffusion coefficient D. On the other hand, for the convection dominated flow, okay, where the characteristic dimension is L and the flow velocity is capital U, the residence time or the physical time will be L by U. So, these are the times. So, chemical time Tc and the physical time or the residence time Tr, these are the two time scales which are important.